Here's part 3 of our chemical bonds review. This will be questions 37 through 49. This will go fairly quick. The other one I know went longer. Let's zoom out here. When we left off on the previous, we were just talking about hydrogen bonds are formed between polar molecules when the partial positive end is attracted to the partial negative end. And then what type of covalent bond this question was asking when hydrogen forms a bond with a halogen. And we just worked through taking hydrogen, and if we take any of the halogens, we find out that it's a it is covalent, but it's very strongly polar covalent when you look at this chart here. So now, 37, we're kind of changing gears slightly. If you have an SO4 ion that has a charge of -2, so I'm just going to go ahead and put parentheses around it and say that that polyatomic ion has a charge of -2. List one element that would be able to bond to it in a 1-to-1 ratio, which is a fancy way to say what element could bond to it that has a +2 oxidation number. So when you look on your periodic tables, all of the elements in the alkali earth metals, they will ionize to form a +2 ion. It's because their 2 valence electrons will leaving them a +2 charge. If we gave you a chart that had, for example, like if it said iron 2, that would let you know, okay, in this case, this particular atom of iron has a +2 oxidation charge. But for the test, it's going to be look on the periodic table and be able to tell that these elements here, when they lose 2 electrons, they become a +2 ion. So it would be any of those elements in group 2. So that would be beryllium, magnesium, calcium, strontium, barium, or radon, because they all have a +2 oxidation number, and that will perfectly balance with a sulfate that has a -2. You just need one of these metals bonded to one of those. What's so special about carbon? Carbon has 4 valence electrons, and it's fairly light. It's pretty light. It can reach out and make chemical bonds really easily. And in nature will take carbon atoms, and they usually pull the carbon out of the air as CO2, and they start ripping it apart and dissecting it and reconnecting it. And what I've drawn here, you don't necessarily need to draw this, but this is the backbone to a sugar molecule. We've got a pair of covalent compounds here, and they'll tend to then attach to an oxygen and so on. But carbon is very light and makes 4 covalent bonds. That's the big deal about carbon. And so it's very common in life. The diatomic molecules, that for example, H2 gas is a diatomic molecule. So that's one of the diatomic molecules that we can have. By that it just means it's the same element bonded to itself. And then the other ones, there's 7 altogether. The little trick to remind you is you go to atomic number 7 on the periodic table, and then you make a little 7. Come over here 3, then you go down 3. So you've got this 7 right here. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine can become a diatomic molecule as well. So that's the memory clue looking on this. And I guess I better go like that so you can actually see it when I fill these in. So we've got N2, O2, F2. Now don't just blindly memorize these, just memorize the clue. There's 7 diatomic molecules. Atomic number 7, turn it into a 7, and then you got to remember hydrogen over there as well. Malleability and ductility. These are characteristics of metals. Malleability means it can be hammered without breaking, so it can be hammered into shapes. Ductility means it is ductile, which means it can be drawn into wires. You can heat it up, and it can be squeezed, if you like, into wires. And what do we mean by squeeze into wires? You get a material that's probably semi-molten, and then you have a plate. This is what they do in factories, have little holes on it like this, and they just squeeze the iron through, and it comes out in long, thin chains that look like wires that we can use. But it just means that you can stretch them and form them into wires. What determines when a bond will be a polar covalent? That means polar means it has a plus or minus end. Or non-polar covalent, which means there's equal sharing of electrons. And so there's not going to be a partial positive, that's the symbol for partial positive, or a partial negative side. So what determines when a bond will be that? Well, it's going to be the element's electronegativity. Electronegativity. The attractiveness, electronegativity, the attractiveness of an element to be able to bond to attract an electron. So the elements up here, the closer you are to fluorine, you'll have this chart on the test, the more electronegative they are. And if you have fluorine in a compound, it's going to tend to be a polar molecule because it's going to hog the electrons. Now, if you had two fluorines, well, if you have two fluorines, they're going to be a non-polar covalent, because if you take the 4.0 of fluorine and subtract it from itself, if you have an F2 molecule, it becomes 0. There's an example where it'll be a non-polar covalent. But it depends upon the difference between electronegativities. So right there, out here so you can see. So the answer to number 14 is right there, difference in electronegativity range. So let's use this chart. Let's do some predictions here. So we've got LiF. Well, you look on here, Li is 1, has electronegativity 1. Fluorine has 4. So 4 minus 1 equals 3. And on this chart, if it's greater than 2, it's ionic. Makes sense, a metal and a non-metal. Next one, we have Na3b, which is boron. So we don't have to worry about the 3. We just have to look up that Na is 0.9. And then boron is 2. So 2 minus 0.9 is going to end up being 1.1. And when we look on our chart, it's going to be a polar, very polar covalent, because it's just in this range right there. So polar, which means it has a plus and a minus end, and it is still covalent. They are sharing, it's just unequally sharing. The bromine has a higher electronegativity, it's hogging the electrons. Now oxygen over here, since we have in diatomic molecules, they have equal sharing, because if we take 3.5 minus 3.5, it's 0. So 0 is nonpolar, and it's still covalent because they're sharing electrons. H2O, hydrogen has an electronegativity of 2.1. We're going to subtract that from oxygen's 3.5. And when we subtract those, we get, that's going to be a 0.4. So 1.4 is the difference in electronegativity. And on this chart, 1.4 would be in here. It's very polar covalent. And that should make sense. Water is very polar. It has, the oxygen end of it is partially negative. The hydrogen end of it is partially positive. We use this Greek symbol sigma to represent that. Or we can use a plus arrow with an arrow attached pointing to the negative end. Describe the bonds between molecules in solids, liquids, and gases from weakest to strongest bonds. Well, it's the bond energy, and solids are held in a rigid, solid form, okay, in a locked pattern, and it takes a lot of energy to keep it. It takes most energy to keep a material at room temperature and solid. Now, liquids, okay, liquids have medium energy. They're kind of the medium bonds. And we're talking like at room temperature here. So things like alcohols and such like that, and water, it doesn't take, they're loosely held together. And then gases have the weakest bonds because it doesn't take much energy. They're free to move around. So it goes from high with the solids energy to keep them locked in a solid pattern. Little less energy. They've got to stay. It takes energy to hold them close together, but they're free to move. And then gases, the particles are far apart. It's the weakest energy to hold them together. And we're ending here with electronegativity study. Nitrogen we want to do the electron configuration, excuse me, of nitrogen. And so, well, for nitrogen, it has 7 electrons. You got to look that up on the periodic table. Silicon has 14 electrons. That's just from looking at their atomic number on the periodic table. Chlorine has 17 electrons, and sodium over here got squished out. It has 11 electrons. And use this chart right here. It'll be provided for you on the test. We need to fill out 7 electrons. So what we're going to do is, let's see, for that first one, 1s. Now s orbital is going to hold 2 electrons. Then we're going to fill in the 2s with its 2 electrons. Now we're on the second arrow right here. Now after we fill in the 2s, now we're going to fill in a 2p. Now they can hold up to 6. So we're going to write 2p, but we only have 7 electrons in nitrogen. We've already filled in 2, so we're only going to have 3 electrons in the p, so it's 2p3. For our friend sodium over here, it's going to have 11 electrons, so we're going to follow this pattern. So 1s2, 2s2, 2p. Now let's see, it's got, so 2p6, 7, 8, 9, 10. We're at 10 electrons, so we need 1 more electron. So the 2p, the next one to go is going to be right here. It's going to be the 3s with only 1. It's got its orbital half-filled, 3s1. And you add these up. 6 plus 1 is 7, 8, 9, 10, 11. That's how you double check. And then silicon. It will be following this pattern. 1s2. Then we're doing 2s2. Then 2. Okay, let me see here. 2s2. Now we're doing 2p6 and 3s2. Now we're at 12 electrons, so now we need a total of 14. So now after the 3s, we're going to put in the 3p orbital sublevel only 2 into there. And then for chlorine, you've got 17 electrons. So let's see, we're going to have 1s2, 2s2. I'm just following this pattern right there. Now we're going to fill the 2p with 6, and then the 3s with 2 electrons. 6, 8, 10, 12. We've got 5 more to go. So now we're done with the 3s2. We're going to fill in the 3p. And let's see, we're at 12. We need 5 more electrons. 3p5, simply 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. We're done. There's the electron configuration for chlorine. On these over here, you were supposed to just name the element. I accidentally covered up the question. And these are easy. You just count the electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25. 25 electrons. And on your periodic table, atomic number 25 is the element manganese, Mn. So on this one over here, we've got 2, 4, 6, 8, 10, 12, 14, 16, 18. Only 20 electrons this time. So that's going to be the element calcium. 20 electrons is the element calcium. Use the off-bow diagram at right. What element is shown? Just add up the electrons and look on the periodic table. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, I know there's 30 there, so that was 20 here. So, excuse me, there's 10 here, so that's going to make this 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. We add 10 more, that'll be 31 electrons altogether. And on the periodic table, atomic number 31 is going to be gallium, Ga. That's the element gallium. What elements have an electron configuration below? Well, just add up the electrons here, these superscripts, 3, 4, 5, 6, 7. 7 electrons is nitrogen. Look on your periodic table for atomic number 7. 4, 5, 6, 7, 8. 8 electrons is going to be oxygen. Now, there is going to be a question. I forgot to put it on the review sheet. How about if we ask you for the electron configuration for nitride ion, N-3? Well, the first step is going to be just like it was plain old nitrogen. You write out what its electron configuration would be. Okay, so it's going to be this one right here. But if it's nitrogen, now I'm going to do the Lewis structure so we can get a visual. Nitrogen needs 1, 2, 3 more electrons. I'm drawing negative charges here to represent the electrons in there. So if it's gaining 3 electrons to make it this -3, then we've got to add 3 electrons to the regular nitrogen to change it into nitrogen 3. So nitrogen 3 minus would be 1s2, 2s2, 3p6. Now it thinks this is the electron configuration for neon. It thinks it's neon. It just has this -3 charge associated with it. So ask me if you're not sure. On the test, always ask. Last question. Yay. You don't have to do the rest of these. We're not doing periodic table review on the test. Draw the simple diagram for an s orbital. Okay, that would be spherical. P looks like what we call either a dumbbell shape or, if you like, an hourglass shape. Yeah, they can be oriented different ways. And the d orbitals is going to be like 2 of these overlapping. It's going to be kind of like this. So I guess we could call this a spherical shape. S-P-H-E-R-I-C, spherical. This can be hourglass or dumbbell shape, like when you're working out in the gym, dumbbell shaped. And then over here, I guess we'd call this a clover shape. Now there is one that kind of does have the dumbbell shape with a ring around it, but we're not going to give you the exception. So there's the shapes. There you go. Finished. Done.